Again, welcome to Precalculus. These lectures cover the log functions and their properties. Our main objective is to use and also apply the definition of log functions. We're also going to learn how to graph and evaluate log functions using the properties of log functions and also using the change of base formula. So let's start with the definition of a log function. Here we said if a is greater than 0, and also a is not 1, which means a will start from 2, then y equal to log base a x is a log function. So again, we read it as log, the a is a base, and x. So y equal to log base a x is a log function. And the domain also is that x should be greater than 0. The base is a, as we said, and also is defined by a to the power y equal to x. So this means we can transform a log function to exponential function, or exponential function to a log function. So a to the power y equal to x, which is exponential function, is the same as y equal to log base a x, which will be the log form of the function. So from the definition, we know that log base 381 is equal to 4 because 3 to the power 4 is 81. So in this case, we say 4, again, is the exponent to which we have to raise the base 3 to obtain 81. Again, from the definition, we can see that log base 381 equal to 4 is the same as writing base 3 to the power 4 is equal to 81. Now, the a is called the base. So in both log a, which is log base ax, equal to y, and also a, the exponential function, a also is a base. A raised to the power y means y is the exponent and a is the base, equal to x. So y is the log in log base ax equal to y. And the exponents in the exponential form, it will be a to the power y equal to x. So here we say a log is an exponent also. Now we have a table here giving us some example. So we have the log form and also exponential form. So log base 10, 100 is equal to 2 is the same as saying 10 to the power 2 equal to 100. So the log base 10, so the 10 in exponential form, the 10 also is a base, and 2 becomes the exponent, which equal to 100. Now next we have a log base 10 0.1. That's equal to -1 because 10 to the power -1 is equal to 0.1. Log base 2x equal to y is the same as writing it in exponential form. 2 is the base, so 2 to the power y equal to x. And we have a special cases here. Log base a 1 is equal to 0 because a raised to the power 0 is 1. And log base a equal to 1 if a is greater than 0 because a to the power 1 is equal to 1. So let's try an example here. Here we are going to graph a log function y equal to log base 2x. So here it's up to us. If base 2 is easy to calculate, then we may use any x interval of values, then we find the log base 2. For example, if s is 1, log base 2, 1 will be the y value. If s is 2, log base 2, 2 will be the y value. But now, since log base 2 is very difficult to find and it takes time, we can convert this log function to exponential function, which will be more easy for us. So now we can say that 2 to the power y equal to x. And we may take any value, any interval of y, let's say from -2 to 2. Then we look for the value of x. Then from there, we can use the table to plot the graph. So that's what we did here. We change y equal to log base 2x to x equal to 2 to the exponent y. Because now this is more easy. So we take any y value, the interval will be from -3 to 2. So let's assume, for example, when y is 0, s is 1, because 2 to the power 0 is 1. When y is 1, s is 2, because 2 to the power 1 is 2. When y is 3, 2 to the power 3 will be 8, so x will be 8. So we come up with a table, then we can plot each point. And this is the form, the graph. Next, from the definition of the log also, we see that every log has a base. So most applications of log involve logs to the base of 10, which is the common logarithms, or we have the natural log, which is the log to the base of e. And these two, log base 10 and log base e, is more common in our calculators. So let's see an example here. We say here, if $P is invested for t years at interest rate of R, compounded continuously, then the future value of the investment is given by S equal to P times E raised to the power of R and T. R will be the rate, T will be the time. Now, the doubling time for this investment can be found by solving for T in S equal to P to the power RT. So since we are doubling, it means the S is equal to 2P. So here we want to find how long it will take for us to double our investment. So here we have 2 equal to E to the power RT. So since T is an exponent, we can convert the exponential function to a log function. So 2 equal to E to the power RT is the same as writing log base E, because the base is E, which is natural log. 2 equal to RT. So we get log base E 2 equal to RT. Our goal is to find T. So T equal to log base E times 2 over R. Because R is multiplied by T. When you cross the equal sign, it's going to divide. So our formula will be natural log 2 divided by R. So here we should know that if the interest rate is R equal to 10% compounded continuously, then the time required for the investment to double is natural log 2 divided by 0.10, which roughly will give us 6.93. So it will take almost 7 years for our investment amount to double. So here we say in general, we can approximate the doubling time for an investment at R interest, or the R percent, which is the interest rate, compounded continuously with 70 divided by R. In economics, this is called the rule of 70. Now, next we're going to graph y equal to natural log x. Now, this time, I'm not going to change it to exponential function, because natural log s is easy to find in our calculator. So we can say, okay, when s is 0, natural log 0 is what value? When s is 1, natural log 1 is what value? When s is 100, natural log 100 is what value? That value will be the y value. So we can use the natural log s, the log function, to plot our graph. And that's what we have here. X and then y equal to natural log x. So we start from 0.05. And then the natural log s will be negative 3.000. Then we have 0.10. Then we're going to get a natural log 0.10. That will give us negative 2.303. So the graph of a log function, here we say that y equal to log base a x when a is greater than 1. Intercept will be 1 and 0. The domain will be all the positive real values, and also the range will be all reals. The asymptote will be on the y-axis, which will be the negative half. So now let's go through the properties of log. So here we say in general, we say that when that y equal to f at x and also y equal to g at x are inverse functions if whenever the pair AB satisfy y equal to f at x, the pair BA also satisfy y equal to g at x. Furthermore, again, because the values of x and y coordinates are interchanged for investment functions, their graphs are reflection of each other about the line, which is y equal to x. So we can say that for a greater than 0 and also a not equal to 1, the log function will be y equal to log base ax, which can be written in exponential form as x equal to a to the power y. So the log function y equal to log base 10x. Now, when we don't have any base and we have log, it means the base is 10. So y equal to base 10x is the inverse of the exponential function y equal to 10 to the power x. Now, the graph of y equal to log x and y equal to 10 to the power x are also reflection of each other about the line y equal to x. So here we have again some values of x and y for these functions are given here. We have a coordinate 10 and 1003. The first value always should be the x value and the second value will be the y value. So y will give us log base 10x, which is the same as log x. So when we plug in the value 1003, we get 3 equal to log 1000. Then we have 102, which will be 2 times log 100. And 1/10, -1 will be -1 equal to log 1/10. Now, if we have y equal to 10 to the power x, then 3 and 1000 will be 10 to the power 3. 200 will be 10 to the power 2. So next, when we graph the functions, this is what we get. So the first function, y equal to 10 to the power x, is in this here. Then y equal to log x, and also the constant value, y equal to x. Now let's look at our first log property 1. And it states that a log base a to the power x will give me x, because we have a for the base of the log, and also we have a. So more or less like we cancel a and a's, then we get x. Now we could also going to use the property 1 to simplify each of the following. So here we have log base 4 to the power 3. So this will give us log base 4 to the power 3 will give us 3. The 4 will cancel the 4 here. And when we check here, we can see that 4 to the power 3 is equal to 4 to the power 3. Now, when we have a natural log e to the power x, we know natural log e is the same as log base e. So we have log base e times e to the power x, and our answer will be x. So now we move to the special cases of log property 1. Now, if we have the exponent as 1, a to the power 1 is the same as a. Also, we know that a to the power 0, the answer will be 1. And that will move us to the log property 2. 2 said if we have a greater than 0 and a not equal to 1, then a, the base, to the power log base ax is the same as x. So again, a to the power log base a times x is the same as x. Now here we're going to use the 2 property or the second property to simplify each of the following. And as we can see here, the property said a to the power log base ax is the same as x, or is equal to x. So here we have 2 log base 2 4. So we can check the term here. Log base 2 4 is equal to also log base 2 4 here. So the first thing we do here again, we have 2 log base 2 4. Now, the 2 here will cancel the 2 here, so the answer will be 4. Same thing in our second question, we have e is a natural log base e. Natural log here is log base e. So if you have e raised to the power log base e, the e's will cancel, so the answer will be x. Now the next we have the property 3, which says that if a greater than 0 and a not equal to 1, then m and n are positive real numbers. Then we can have log base a m times n is the same as log base a m plus log base a n. Now the same thing applies to division. Log base a m divided by n, it will be log base again a m minus log base a n. So let's use this theory to solve these 2 problems. First, we're going to find the log base 2 4 times 16. But we know log base 2 4 is 2 and log base 2 16 is 4. So log base 2 4 times 16, we are going to expand it to log base 2 4 plus log base 2 16. Then we know log base 2 4 times 16 is the same as log base 2 64, which will give us 6 again. Now with b, we have a natural log 77. But when we look at the question, they gave us 7 equal to 1.9459 and also 11 equal to 2.3979. So here we have a natural log 77, which gives us natural log 7 times 11. So here we can say that natural log 77 is the same as writing natural log 7 times 11. Why we chose 7 and 11? Because that's what is in the question. 7 is 1.9459, 11 is 2.3979. So again, when we solve this problem, instead of natural log 7, we put 1.9459 plus natural log 11 was 2.3979. So the addition of 1.9459 plus 2.3979 will give us 4.3438. So next will be our 4th log property. Now here we say if we have a log m divided by n, then it will be log m minus log n. So let's see an example. Log base 3 9 by 27. I can choose any base, but most of the time we're going to choose natural base or base 10 because those 2 can be used. We can get their values in the calculator. So let's look at the first question. Log base 3 9 divided by 27. So this is the same as writing log base 3 9 minus, again, log base 3 27. So here we solve the problem. 9, 3 squared will be 9, so the answer will be 2. And here is 3. 3 cubed is 27, so it's 3. So our next rule, we said log base a m to the power n is the same as writing n times log base a m. So example here is if I have log base 3, 9 square, I can write this as 2 log base 3n. 2 log base 3n. And our answer will be 2 times log base 3, 9 is again 2. Why? Because 3 to the power 2 is 9. So here again, we are using the formula log base 3, 9 to the power 2. So it can be log base a, m to the power n. So n will be in the front. Then we have the log base 3, 9. So 2 times log base 3, 9. Log base 3, 9 will give us 2. So our final answer will be 4. Now let's look at the second one. Natural log 8 to the power negative 4. So we can write it in this form, negative 4, natural log 8. Then from there again, we can solve the question. Go to the calculator, we look for the value for natural log 8. Then whatever answer we have, then we multiply it by 4. And that will give us negative 8.3176. So our last section will be the change of base. Now, this is how change of base works. I have a log base a, b to the power y. Now, I can change the base to any base. Most of the time, we are going to change the base to natural log or base e, and also base 10, which is regular log. So here we say log base a, b to the power y is the same as writing, again, log base a, x. Now, here we have again log base a, b, y. We use the rule, so y will be in the front, so it will be y log base a, b, which again equal to log base a, x. Then to find y, it will be log base a, x over log base a, b. Now let's see how we can use the formula. So this is the rule again, log base b, x. I choose any log. Here we decided to choose log a, so log ax over log a, b. So let's use this formula to solve this problem. We have log base 715. Evaluate log base 715. Now the base 7 is difficult to use the calculator. It's not. So I will change it to either natural log or base 10. So we decided to use natural log. So log base 715 is the same as saying natural log 15 divided by natural log 7. Then here, we can use our calculator to find natural log 15 and also natural log 17. Then we divide the two values, and this will be our solution. So again, change of base, log base 7, 15. I can say, okay, log base 10. I change it from 7 to 10. Log base 10. Then log base 10 of 15 divided by log base 10 of 7. So that will be the conclusion of this lecture. Again, these lectures, we learn how to, again, evaluate log functions using, again, the log properties or rules. Thank you.